so the knapsack problem is a very famous and very important DP problem. Here, suppose the question is basically like this: you have a box, say there is a box, and the capacity of the box is say W, and there are some items. Let's say there is one item which has a weight of say small w equals to 5, and its cost or its price say p equals to 10. Similarly, there is another box, several boxes are there. So the question is, you have to put the some of the smaller items into this box such that the total weight summation of small w is equals to capital W, and this price value, the price of the items which you put in the box, will be maximized. Is the question clear? So, what is the very basic brute thing that we can do here? The very basic thing is that we can check all possibilities. Suppose there are say n small items. Let's show them as an array. Let's say the items weights are say 5, 2, 10, 12, 1. The price say 10, 20, 30, 10, 50. And the maximum capacity is say, let's say 50. Yeah. Yeah. 50, 50. So the brute force thing that we can do is checking all the options, uh, and that will essentially give us 2 to the power n combinations. The time complexity will be O of 2 to the power n, because each item has two options, whether we can keep it or we will not keep it. So each item has two options. There are n items, so there would be 2 to the power n options. And this is very easy implementation, but this is not very efficient. 2 to the power n, so anything beyond say 20, 15 or 17, the value of n, you will get a time limit exceeded. So the efficient way of doing this problem would be dynamic programming. So the idea behind the dynamic program is that for each, let's say, uh, we will check for all weights from 0 to capital W, from 0 to capital W. We will check that if we put the ith small item, what is if we uh, either put or do not put the ith sub item, what is the maximum price that we can achieve. So let's see with this example. Here, the first item is weight is W, sorry, 5. So if we keep this thing, then the remaining weight that we have would be 10. and the price would be, say, uh, is 10. Now, uh, okay, so let's make the table only that. So in this case, here in the columns, we keep the weights from 0 to capital W here, which is 50. And in the rows, we keep the indices of or the number of smaller items. So 0, 1, 2. In this case, it is 0, 1, 2, 3, 4. So for each state here, dp of I comma j, we will check that if we can either place or we do not place the ith item, and the total weight up to that thing would be say here j. So essentially we are placing here some combinations of items from 0 to I, and the maximum or the total weight here would be j. So if we want to put the ith item there, and we want to uh, maintain the sum to be j, then we should keep in mind that all the sum of the weights of the remaining items would be I minus, let's say, the weight of I, isn't it? Then only the sum, uh, sorry, not I, it's j, j, uh, yeah, j, j minus the weight of j, then only the total sum would remain j minus w of I plus w of I, which is j. So here we can think about one transition here, right? So dp of I comma j, there can be one transition here would be say the and here we would keep the prices. So dp of I minus 1 j minus w of I plus price, say p has the prices of I. So here essentially what I said, we are doing the same thing. So we are getting the maximum amount, maximum prices that we got uh, after we put j minus w of I. The total weight was j minus w of I. And why we are making it I minus 1, and why not I? The thing is that uh, at some point when we process dp of I and j minus w of I, we could have kept the item, we have chosen the item, say I. So, but we can only choose the items once. So if we have, if we had written here dp of I and j minus w of I, then there was a possibility that we could have taken the ith items twice or more than that, which is invalid according to this problem. So dp of I minus 1 j minus w of I here signifies that the maximum price, if we had put uh, any combination of I minus 1 items, say I is here, this one. So any combination of I minus 1 items such that the sum is j minus w of I, and and the price is maximum. So we got that, and since we are putting or choosing the ith item, so the price has to be included here. So we are adding p of I. But there is one another thing, that we cannot choose the ith item here, right? So in that case, what will be the other case? It can be that uh, the sum should remain j, the total sum should remain j, but we are not choosing the ith item. We are not choosing the ith item. So it would be essentially dp of I minus 1 and j. Dp of I minus 1 j here signifies any combination of I minus 1 items such that the sum is j and the price is maximized. Uh, this thing, so one is here we are choosing the ith item, and the other we are not choosing the ith item. So we have got the transition formula. So the transition formula here is dp of I j is equals to maximum of maximum means here we can choose any one, either we choose or we do not choose, and we want the maximum price, so we will be here making maximum of dp of I minus 1 j minus w of I plus p of I, comma dp of I minus 1 j. One important thing that you should keep in mind is that this thing, if suppose the weight of the item, say w of I is, say 12, in this case 12, but we are processing some j, like let's say 7. So the total sum would be j equals to 7. We can, so it is quite uh, evident that we cannot put the ith item which has a weight of 7, maintaining that the total weight will be 7. So this is essentially a very bogus idea. So we should uh, keep one if else statement, that if the weight is greater than the maximum weight that we are processing currently, then we can not take the ith item no matter what. And so this thing becomes null or zeros, let's say. So there is only one option, that we do not keep. So this is like this. And what is the base case here? This is very important in this knapsack problem. Let's say we are not, there would be two base cases essentially. What happens that we do not choose any item. um, how many possible ways of not choosing any item such that the sum can be anything, right? So it is essentially one. The number of ways of not choosing any item is one. So here in the first thing, if uh, no matter what is the weight, the num uh, the number of ways, the price, here we are choosing the price. So these things would remain zero. Actually, the number of ways would be one, and the maximum price would be zero. So all in the first cases, if let's say uh, we are not choosing anything, the prices would be zero, and we would not check this condition. If we are in the first row, which essentially indicates that we are not choosing any item at this moment, then there is no point in checking this transition function. So if it is in the first column, we will just put zero. And there is this thing that if we are in the first row, which means the total weight is zero. If the total weight is zero, no matter and if one thing is that if any of these wi is zero, then there is a possibility. But since this is the weight of some item, it cannot be zero. So since all weights are positive, then there is no way that we can add those items into a list and make the sum to the maximum sum or the total sum to be zero. So this thing also becomes zero. So these are the two base cases, and from all uh, rows afterwards, we will check this condition, and then what will be the answer? So the answer would be, so the answer is the total weight is J equals to W, and we have chosen some combination of items from I equals to n items. So the answer is dp of W n, or here it is the opposite, because I've taken the rows to be different. So this is would be just reversed. So is dp of n and W. So is this thing clear? Any questions or anything? Hello.
Yes, yeah.
Okay. So anyone has any questions about this knapsack problem? No one has any problem. So I also asked in the group that if you have any problem in any question, or if you want to discuss the questions that want to discuss those questions, we would be discussing it here. But no one actually asked any questions. So I think that either you are able to answer all the questions that you are attempting or not attempting at all. There was one question which was greedy. So now we will discuss one very simple problem related to knapsack, which Anish will discuss. Anish?
Yes, yes.
Okay, so Anish
Am
will
I
now
audible?
discuss.
So as Sonak was discussing about the knapsack problem, so that was basically a 0 1 knapsack problem, right? Means what do I mean by 0 and 1 is that either you can take the element, or you cannot take the element. Means either you have to take the full element or you can't take the element. So there is another kind of knapsack which is pa-
Anish,
hello, hello,
one
hello.
second. Hello, yeah, one second. I will tell one more thing. Yeah, so related to this knapsack, that the idea I said, can anyone tell me about the time complexities here? Anyone? Is anyone there? Okay, so I don't think that you guys are interested in the thing. So yeah, Anish, continue.
So basically, what there is another kind of knapsack apart from 0 1 knapsack, that is fractional knapsack. So what you can do here, basically you can take a fraction of an object here, right? So for example, if you have objects such that the weight of the object is say 10 and the value of the object is 5, and then another you have 9, 4, like this. So what you can do is that you can take a fraction of an object. So if you take a, let's say you take a 0, means 5, 5 weight of 5 of this object, so you gain a value of 2.5 here. Means you are taking 50% of the object. So also again, you if you take a weight of 2, then you gain a value of 1, so that is 20% of the object. So that means you don't have to take always 100% of the object, like in this case. In this case, either you have to take 100% of the object or 0%. Means either you have to take the object as a, means the full object, or you can't take the object. Yeah. So but in fractional knapsack, you have the option of taking a percentage of the object. So can anyone tell me that whether we will apply DP here or greedy, and why? Anyone? Means you can be wrong, so it doesn't matter. You can just try. Means whether we have to apply greedy here or DP. Is the question
Greedy.
clear? Uh, is the question clear? Means what is fractional knapsack? Someone just spoke. Who was that?
We are greedy.
Means why you can tell? Means can you give the reason why greedy will work here?
We can do price by weight. Then we can get for uh,
Yes, yes. Means what you are telling that we will calculate the ratio of
yes,
value by weight, and we will take the highest ratio. Means highest item having such a
yes,
ratio.
yes, and
Yeah,
then we will start filling that way.
yes,
Whichever
this
has the
works.
highest ratio,
So
that
why would it not work here? Why we had to apply DP here? Means
because it may happen that something with the highest ratio we are using it, but at the end there are some spaces left. Uh,
yes, yes,
uh, so we cannot take that way. So maybe we can fill it by other
yes.
things.
So basically, there can be unused space left, which we could have utilized in a more optimized way in 0 1 knapsack at the end. So in fractional knapsack, so we can just keep filling the objects which have the highest value by weight ratio, and then we can fill them in a greedy way till we fill the whole container or box. So this is a very common problem which can come in interviews. Means in one of the mock interviews, I was asked this question, means why this will work and why this will not work. So it was, so now we can move to a problem which utilizes 0 1 knapsack. So you are given an array. Let's say the array is 1 2 4 9. So the sum is 3 7 16 and let's say 5 and 8. So you are given this array. So you have to tell whether the array has a subset whose sum is equal to the half of the sum of the total array. So what do I mean is that if S is the sum of the total array, you have to find a subset whose sum is S by 2 and S is even, mind you. Means you have to find whether such a subset is present or not. What do I mean by subset is that, for example, a subset can be comprised of the elements from the array. So 1 and 5 could be a subset. 1, 2, 5 and 8 could also be a subset. An empty array could also be a subset here. Means you people have done a sets in class 11 and 12, right? So you should know what a subset means. So a subset is nothing but a set, means a set of numbers which could be formed by using the elements of the array. So you have to tell whether such a subset occurs or not.
So we can just like for every element we have two options to add it in our set or not to
Yes.
add it. Then in
One
that
of
way
the
we
very
can check.
base cases, first you can tell, means in which case the answer will always be no.
Like if when we take an element and the element is odd, or like we take 5 but 5 is odd,
Yes.
then that can be a base case.
No, I
If
am.
the value of the element is greater than S by 2, then we will not take.
Yes, no, I am telling. I am telling that in which case we can surely say that the answer will be no. Means when we are given the array, means by seeing the array only, in which case you can directly tell whether the answer is no or not.
So size of the array is 1 when
Yes, one is the size of the array is one, right?
And element is odd, like
S has to be even, right? Otherwise you can't form a subset. So if the sum of the array is odd, so the answer will be no, right?
yeah,
Is this clear? If the sum of the array is odd, then we can't have a subset whose sum is S by 2, right? Because S has to be even here. Hello.
yeah.
So these are the two base cases. So if the sum of the array is odd or the size of the array is 1, so you return no. So these are the very primitive or trivial cases. So now we can go for a more generic solution. You can use the idea of knapsack. So can anyone come up with an approach, means how we can use knapsack here? What will be the DP states and the transitions? Anyone can come up with any approach. It doesn't has to be right. You can be wrong also. Anyone? Means if you have understood the
Like,
knapsack problem which was
we
discussed by Sounak,
uh,
means you should come up
we
with
can
yes, yes, yes. Tell.
form a knapsack of sum and the elements. Like,
Yes, yes. Means what will be the states? The first state will be
first state will be the sum, and the uh, second will be
means
the each
yes.
element.
Means you can think in this way. Means how can we form means reform this question so that the question becomes a knapsack problem. Means how can we break down this problem so that we can directly apply knapsack here. So basically what we can think of is that we have say the length of the array is n, so we have n elements and we have to take among n elements such that the weight or the sum of all the elements that we have taken is say s by 2. We can denote s by 2 2 as t here. So what was the knapsack problem, right? We had to take some elements, say we have to take some elements out of k elements, and we were calculating for a particular value, right? In knapsack dpk value, right, like this, where we were taking some elements of out of the k elements, and the elements which we took, the sum of the values of that elements were this. So in this problem, this is nothing but this will be something like this. So we take some of the elements from the first I elements, and the elements which we take will have the sum this. So these are the two states here. Someone was telling that one state will be the sum and the another state will be the number of elements. Yes, he was correct. So can you continue how we will do the transitions? It will be very similar to the knapsack transitions that we just discussed by Sona. Here also we have only two options for every element. Either we will take this element or we will not take this element. So there will be two kind of transitions. For one, if we take the ith element, another if we don't take the ith element. So if we take the ith element, so what will be the transition?
So we can like set something to 1 or 0.
Yes, means we will set one if it's true or zero or false. I am saying how we will calculate this state from previous states.
Like uh,
dpi minus 1
Yes,
dp I minus
sum
1
minus
sum
sum minus. What was the previous sum if we
I
before we are
sum
taking the ith
minus
element?
sum minus I min like the ith element was sum minus
ARRI,
arr I think arr I minus 1. Wait.
I minus
Yeah.
1, y minus 1.
No. arr I minus 1. I mean,
This you are telling.
no. I'm telling sum minus arr I minus 1.
Oh. No, we are taking the ith element as zero index. This is zero index, right?
Okay.
So you don't have to think about indexes right now.
Okay.
So it will be error I, right?
Yeah, yeah, yeah.
Another option we
Plus,
have if we don't take the ith element, right? So in this case, what will be a transition?
dp I minus 1 sum.
Yes. So these are the two transitions, and if any of this previous state is one, then this state will also be one. dp n sum equals to 1 if we can obtain a subset which has sum x, say, or 0 if we can't obtain a sum of x using any subset, right? We are defining dp in this way. So if any of this two state is 1, so dp I sum will also be 1, because if this is 1, we will take the ith element and we will obtain a subset which has some sum. And if we already have a subset with the sum sum, then we don't take the ith element, then also we are having a subset which has this sum, right? Is this clear?
Yeah, bhaiya.
So uh, so for the final answer, what we will check means which dp value we will check for the final answer. Means did you get the question? What I am asking means which element in the dp table or state which we will check for the final answer, means what we have to ultimately find. Here dp nx denotes that we take some elements from the first n elements, and the sum of the elements which we take is x. So this is the definition of the dp table. So now can anyone say that which dp means which element in the dp table we will consider for the final answer, means what we have to ultimately find? We have n elements and we have to obtain a sum of s by 2. So which dp state we will check for the final answer? So if we will check dpn s by 2, right? So if this is 1, then the answer is yes, means we can have a subset whose sum is s by 2 and the numbers are from the first n elements. So the answer will be yes if this state is 1. Otherwise, if this is 0, so the answer will be no. And what will be the base case? dp 0, 0 is also already 1, means 1. Means we if we don't take any element in the beginning, so the sum is 0. So this is always true. Did anyone get, means why we are making this 1? Is there any confusion in the base case? Means why we are considering this, because here we are not taking any element, because 0 means we haven't considered any element, so we are not taking any element. So this is basically the empty subset. So the sum of the empty subset is 0, so this will always be true. So is there any question in this uh, problem, or any other approach you can think of or optimize this? So is the solution that I discussed is clear?
Yeah, भैया.
So any questions on this? So I guess no questions are there.
Here I would give you a home task. So what Anish did was a two-state DP. If you can try at home in a one-state DP,
Means
if
the
you can.
time complexity will be the same. You can optimize the space complexity here. Means the time complexity will remain n square, but you can optimize this to a O of n space. So since no one has any more doubts or questions, I think we can end the session here. So okay, we are ending the session.